So, good evening, everyone. So today, I shall talk regarding to unit number 2 of computer organization. So, look at this here. Unit number 2 does have this information. So, digital logic circuits. Let me say combinational circuits, and what are different kinds of combination circuits which are available, and what are the implementations of those combination circuits will be discussed today. Okay, most probably I shall discuss half adder, full adder, and multi-bit adder will be discussed with you. Okay, so up to this one, I shall have a chat with you. So things will be permitted me. I will discuss more also. Okay, however, so let's get started with MS Paint. So here, as far as combinational circuits, normally in digital logic circuits, we do have two different types of circuits which are available. One is combinational circuits, and second one is the sequential circuits. So combinational circuits are normally depends upon, if you take any combination circuit, so combination circuit will be seen something like this. Any kind of combination circuit will be seen something like this. Is the block diagram of that combination circuit. We do have much number of inputs. You do have as much as many number of inputs will be there. All these things will be considered as inputs, and we do also have as much as many number of outputs as well. Sometimes many number of outputs, sometimes very few number of outputs might be there. However, outputs are many, not exactly so one or two. So they are supposed to be many here. So therefore, always the inputs, whatever the inputs you are supposed to consider here, whatever the inputs you are supposed to consider here, a moment please, yeah, whatever the inputs you have considered here, all these inputs will be connected to, so this outputs here, and these are called as the outputs. These are called as the outputs here. And here in combination circuits, major point to be remember here will be the output variables must be depends upon input variables. Okay, so for any point of time, for any instance of time, so the input output variables will be always depends upon this input variables here. So that is the point where exactly you need to remember in terms of combination circuits here. And the combination circuits will be always connected to the input of the devices, and the outputs will be given from the specific inputs here. Let me discuss first combination circuit which is available for us. The first combination circuit within your syllabus is what is that adders. So as far as your syllabus, it is not available with you as adders, but I'd like to discuss with you half adder is the one of the first combination circuit which is available with you. So half adder will be always perform operations by using two different bits. If you have two different bits are there with you, then what are the outputs of that particular adder will be decided by the half adder here is. So let us consider, if you take half adder, let me consider here. So you do have only two inputs are there with you, A and B. So will be there with you. Half adder will be always provides so A plus B as its outcome here. Its outcome here. So as far as this particular half adder, you can consider here. So this is 0 0. So 0 1 1 0. So finally 1 1 here. And this A plus B will be, let me retermed as, let me reconsider this A plus B into, so in two formats. One format will be considered as the sum. One is the sum, and second one is the carry here. Sometimes you may be have carry, sometimes you may not be have any kind of carry here. So 0 plus 0, sum will be equal to 0, and the carry will also be equal to 0. So let us consider 0 and 0 will be taken. If you add these two together, so 0 plus 0 will be 0, and you don't have any carry here. So that is the meaning of this one here. And 0 plus 1, so if you take 0 plus 1 here in the sense, sum will be equal to, so 1, and there is no carry here, no carry at all. And 1 plus 0, so here also the same scenario. So 1 will be the sum, and there is no carry here. No carry will be so available here as far as this particular thing. And similarly, if you take 1 plus 1, so if you consider that 1 plus 1 will be taken, so added together, then you do have 1 plus 1 will be actually, as for decimal point of view, it will be 2. And in binary, 2 will be represented as 1 0. 1 0 is the value of 2 here. So therefore, this particular value is going to be represented as far as half adder point of view will be 1 will be the carry. So 1 will be the carry and 0 will be the sum here. So this is sum and this is called as a carry, sum and a carry here. So therefore, if you are trying to perform the operations using 2 bits of information, you might be having this many number of combinations which are available for us. So therefore, to design this particular thing, let us consider the so truth table first. So otherwise outcome table first, then based on that we have to design the half adder here. So 0 plus 1 will be taken as sum is 1 and carry will be 0, and 1 plus 0 will be taken as sum is 1 and carry will also again 0. And here as far as so 1 plus 1, so it will be taken, this is the actual sum is 0 and carry will be 1 here. So here you please understand what exactly this particular so outcome table is. This outcome table will be depends upon so sum of products, SOP only. It is actually so canonical form of sum of products form. Okay, within this sum of products form, so you can see, let me increase the size of the pen. It is 875. Let me take it as a 10,000 because we'd like to draw many number of diagrams here. So as far as this one here, you could see here, so sum will be taken these two different types of locations where exactly if you consider these two here, this is what about sum, and the carry will be taken this particular area. This is so this is the carry area where exactly you are supposed to come across when you are trying to add two elements or two so inputs by this particular combination circuit here. So as far as sum, so sum will be gives you when A will be 0 and B will be 1. This is one condition. And second one will be A will be 1 and B will be 0. And you need to, so probably you need to remember one thing, you might have recall one thing. So that is the sum of products, original form will be, so always if you take A will be the original form will be taken as 1, and its a complementary form, A complement will be equal to 0. So you please remember this, these two. So that what do you mean by this one here in the sense? So A into A complement something like that, or A complement B, otherwise B complement something like that. So original form will be 1 and complementary form will be equal to 0 here. Based on this one, so you need to write the expression here. So if you are supposed to write the expression, so in terms of this particular thing will be seems like this here. So A complement B. So I'm writing this particular expression here plus. So then the second one is this one here. So A B complement. So sum will be gives you this particular kind of expression here. And if you are trying to specify this particular expression, it is always almost all seems something like this. So A exclusive R of B here. So if you take A exclusive R of B, it will be provides so sum of two different types of elements or inputs which will be provided to the so half adder here. Similarly, here you can take this particular thing here. So let me take some other color, then you could understand very easily. So it will be, so let us take this particular carry here. If this particular carry will be taken into consideration, so this carry will be, so both values will be equal to 1, then carry will be 1, otherwise carry will be 0. So therefore carry will be taken something like this, A into B here, A into B. Now you can design. So block diagram for this one is, this is the block diagram. Block diagram is very simple. So let me consider this is a half adder. Half adder. Okay, this is a half adder here. Now this particular half adder will be having two different types of so outcomes. Two outcomes will be there, and similarly two different types of incomes. I mean inputs will be there here. One is A and the second one is B, and one is sum and second one is carry here. This is the carry. And if you are trying to draw, the logic diagram for this particular thing will be, so which is seen in such a form. Logic diagram can be seen in particular form here. So you can see sum will be taken exclusive or of so A and B. So therefore A will be one input and B will be another input. So this is A and B. Okay, then sorry, exclusive OR. So therefore exclusive OR term will be represented like this here. So this is exclusive OR. So which will be considered as sum will be equal to A exclusive OR of B here. And the carry will be taken. So A into B. A into B in the sense, so it will be same something like this. A will be taken. Then B also will be taken here. So if you take these two and combine, it can be produced as carry. So carry will be equal to A into B here. So this is the logic diagram for that particular thing here. Okay, for that particular thing. If you are not interested to draw this particular thing, I mean exclusive OR is not interested to drawn by you, this could also be drawn something like this. This could also be drawn something like this here. And you could draw something A followed by A will be same to this one, and A complementary form will be same to this particular complementary form, and B and B will be this one. So B's complementary form will be, so this one here, this is B complementary form. Now you could able to draw A complement B plus AB complement. So A complement B. So let me take some other color, then it is very easy to understand by you. This is A complement and this is B here. This is B here. A complement B. A complement into B. So it will be taken something like this. And then so A B complement. So this will be, so A and this is B complement. So you could able to draw this one here, and these two will be added together by using a OR gate here. So you could able to draw something like this also, only using AND OR gates. It is the specification. So sum will be equal to A complement so B plus AB complement. So this could also be so drawn here, but people are expecting this particular diagram in our final examinations. Only this diagram in final examinations. To understanding in a better way, I'm giving this particular thing here. To understanding in a better way, I'm giving this particular thing for our so better understanding purpose here. So here right now, I'd like to take so two more. So for the carry, so carry A into B. So this is A, and let me draw some more. Okay, so this is B here. This is B here. So we'd like to combine these two with a AND gate. So this is called as A into B. Carry will be something like this. Both will be eligible. You can able to write both, but most of the textbooks or most of the evaluators are expected this kind of definition. This this kind of logic diagram in our final examinations. This is the expectation of you while taking or writing as so half adder in terms of so logic diagrams here. And of course, this is also correct. This is also correct. We do have one particular logic, I mean, basic logic gates. That gate will be exclusive OR gate. So directly you can draw with exclusive OR. So nothing at all. Both will be same. So this is what about the half adder. Half adder is always trying to perform the operations with only two different types of inputs. Okay, if you have two different types of inputs will be there with you, so obviously you might be having 2 power 2 number of combinations, that is 4 number of combinations which are available for you. And this is called as the truth table for so half adder here. Look at this, always as far as the definition which has been taken for combinational circuits, so always so output will be always depends upon the inputs of so present combinational circuit here. So if 0 0, sum is 0, carry is 0, nothing is there for sum and carry. So 0 1, sum equal to 1, carry equal to 0. Similarly, the 1 0, sum equal to 1, carry equal to 0. And 1 1, so both will be equal to 1, then sum equal to 0 and carry equal to 1. So therefore, outputs of combinational circuits are purely depends upon inputs. Purely depends upon inputs. So, okay, this is what the point which we have to make for so the combinational circuit. Let me say the circuit will be the half adder. Whereas if you go for full adder, full adder is always trying to consider. So there might be having some kind of other so inputs. So let me give you. So full adder can be always used to apply on 3-bit so binary on so 3-bit binary kind of inputs will be there with you. Then it will be gets so added here. So let me draw something for you here. So let us consider C, A, and B. You can take like anything, not only exactly this particular kind of so taken here. So you can take anything here. So whatever the consideration you can take. Some people are trying to join here, I think. Admit. Okay. So ABC or CAB, you can take anything. There is no problem at all. Okay. And then there is a sum and there is a carry. There is a sum and there is a carry here. Okay, so for better understanding purpose, let me take this is ABC instead of CAB. Let me take it as ABC. So that is a better way of understanding. So ABC combinations for ABC. If you have 3 bits, will be there with you 2 power 3. So totally 8 combinations will be available. 8 different kinds of combinations will be gets available. So for you here and here. So if you take so the combinations 0 0 0, so 0 0 1, so 0 1 0, so 0 1 1. So with the 2-bit combinations, everything is over. With the 3rd bit as all zeros. Now let me convert all 3rd bit will be converted into 1. So 0 0, so 1 0 1, so 1 1 0, so all ones. So this is the total number of combinations which are available with you. Now, if you add some kind of addition between or among these 3, so 0 plus 0 plus 0 will be sum equal to 0 and carry also 0 here. Sum equal to 0 and carry also 0. 0 plus 0 0, 0 plus 1 sum equal to 1 and carry will be 0 here. So 0 plus 1, 1, 1 plus 0, sum equal to 0, sorry, sum equal to 1, sum equal to 1 and carry will be equal to again 0. So 0 plus 1, that is 1, 1 plus 1 will be equal to sum equal to 0 and carry equal to 1 here. Please try to operate in a proper way. So 1 plus 0, 1, 1 plus 0, again 1, so sum equal to 1, carry will be equal to 0. 1 plus 0 is 1, 1 plus 1 will be equal to, so let me consider this one as sum equal to 0 and carry equal to 1. Here also 1 plus 1 will be, so carry equal to 1 and sum equal to 0, 0 plus 0 is 0. So this is 0 and here it is 1. And 1 plus 1, so carry equal to 1 and sum equal to 0, 0 plus 1, 1 here, sum equal to 1 and carry equal to 1. So look at this, at this particular places, you could understand one specific issue. At this particular places, these 2 places, if you do understand, so either this place or this place, So A bit will be taken as one more input for the combinational circuit in these two scenarios. In these two scenarios, so combinational circuit might be taking some outcome, some carries will be taken as input to the particular combination circuit here. So if you want to draw this particular combination circuit, so as a block diagram, you can see. So you can write it as let me write this is A. Let me write this is B. 3 bits are inputs are there here. Let me write this will be C here, and two outcomes will be there here. So one outcome will be sum, and the second outcome will be carry here. While writing this one, you please understand one proper issue. You please understand one proper issue. That issue will be, so 1 and 1, so will be there with you. You can understand how this could be gets added together here is, so 1 plus 1 will be, sum will be equal to 0 at this place. So the sum will be equal to 0 and the carry will be equal to 1. Okay, 0 plus 1, so 1 here, sum will be 1 and the carry will be dropped down here. So that is the point which we have to understand. So 1 1 0, if you take this particular thing here, so 1 plus 1, 0 will be the, so 0 will be the sum and the carry will be 1, and 0 plus 0, this 0 plus this 0 will be equal to 0 and the carry is 1 here. What is my interest to be specified here is, sometimes this particular carry, whatever the carry you got, that will be considered as the input here, input of so the combinational circuit, and sometimes the carry will be goes with the output here. So that is what I would like to specify here. Okay, sometimes carry will be goes with the out, and sometimes the carry will be goes with the, so input here. In these two cases, so input carry will be goes for input here. Whereas if you observe this particular thing, or if you observe this particular thing, this particular case, these two cases with what I have drawn with the blue color, if you observe that one, so 0, so 1 1 here. So if you add this one, so you can take this one here, 0 plus 1 will be equal to 1, 1 plus 1 will be, sum is 0 and the carry will be directly goes to out. This could not be taken as input here, directly it will be goes to out. Similarly, 1 0 1, if you take this particular example as well, so 1 plus 0 is 1, 1 plus 1, sum is 0, carry will be goes directly outcome, carry will be goes directly to the outcome here. So therefore in these two cases, so carry directly goes for out, and in these two cases, this particular case or this particular case, carry will be goes as in, and based on that it is going to be added. So therefore, so these are the very important points to be understand by, so what you call full adder, and this is full adder here. And to solve this particular full adder, let me take take the help of what you call Karnaugh map. Let me take the help of the Karnaugh map. So look at this Karnaugh map is 3 inputs are there with us. So therefore the Karnaugh map will be drawn something like this. This is the Karnaugh map where exactly you got here. So totally 8 blocks will be there, or 8 boxes will be there within the Karnaugh map. And this is A complement, and this is A here. So B complement, so C complement, so B complement C, BC, and the BC complement. So if you take this particular thing, as I said in the previous lecture, that is while drawing the Karnaugh maps, how you could specify here. Look at this. So this particular thing is 0, this is 1, this is 2, this is 3, 4, 5, 6, and 7. Some will be available at 1. So 0 and 1, here it is 1. So some will be available at 2 as well. So this is 2. This particular thing is 2 here. And this is 2. And then some will be available at 4. So 0, 1, 2, 3. Here it is 4. And some will be available at 7. So here it is 4, 5, and 6, and 7. This is 7 here. Now, So no one is goes with any full rolling or dual rolling here. Everything will be goes with single rolling. So only single rolling here. This is single rolling. This is also single rolling. This is also because adjacent. So ones are not available here. Everything will be goes with the single rolling only. Since it is goes with single rolling, let me draw. Let me draw all of them as in a proper way. Let me draw all of them in a proper way. So sum will be equal to, let me take this particular thing here, A complement, B complement, C, that is the first value. And let me take this particular thing, A complement, B, C complement. So plus, so let me take this one, A, so B complement, C complement plus, so let me take this one, A, B, C. So this is the particular value here which is available. And now I'd like to take some common and do the some activity here. So let me consider here. Let me take the common in between these two as A complement. A complement will be common. So B complement C plus BC complement. And here let me take here A will be common between these two. A will be common. So A into B complement C complement plus BC. B complement C complement plus BC. Now look at this. So A complement into it is the expression of exclusive R. This is results of exclusive R. So B exclusive R of C plus, so A into, this is the expression of exclusive NOR. So B exclusive NOR, exclusive NOR will be specified something like this, exclusive NOR of C here. Let me consider B exclusive of C will be one component. Let me consider Z will be equal to B exclusive of C, and exclusive NOR in the sense it must be in terms of Z complement. In terms of Z complement, right? So if it is exclusive R, this is exclusive NOR. Exclusive R's complementary form is exclusive NOR. So it will be Z complement. So therefore, A complement into Z plus A Z complement. Z complement. It will be seen something like this. Now I'd like to say A exclusive R of Z here. Actually, substitute the value of Z here. If you substitute the value of Z here, what is the value of this Z here? That is B complement, B exclusive of C. So therefore, A exclusive of B exclusive of C. So this is the so expression for sum. I hope that you do understand. So if so B exclusive of C will be the particular value, that is Z, and Z complement must be equal to B, so exclusive NOR of C actually. B exclusive NOR of C here. B exclusive NOR of C, because it is in complementary form of exclusive R. So therefore, so this will be equal to B exclusive NOR of C here, and you have to substitute the value of, so exclusive R only, because A exclusive of Z has been get out comes here. So you have to substitute the value of Z here. Z value is this one. So therefore, you got the particular value something like this. And try to draw the Karnaugh map for C as well. So C's Karnaugh map, that is carries form Karnaugh map here. So here also we do have. So here it is A and here it is BC. So A complement A. So B complement C complement. So B complement C, BC, and BC complement. Look at this, where exactly C values will be 3, 5, 6, 7. 3, 5, 6, 7. Look at this 0, 1. This is 2. Here it is 3, 4, 5, 6, and 7. You can observe this one here. So this is one rolling. Let me take some other color. You could understand very easily. So this is one particular rolling, dual rolling. This is another dual rolling. This is another dual rolling. You can see this one here. Totally 3 rolls are available here. Instead of taking single roll, if you take single roll, you do have three terms or three elements. Whereas if you take dual, we have only one. Sorry, we have only two here. So for the first one, let me consider for this particular thing, a plus a complement is equal to 1. So therefore, it will be considered as BC. So BC plus for the second one, this is the second one here. So a single row and the two columns have been participating. So here B complement plus B will be B complement plus B will be goes 1. So therefore AC will be the next value. And if you take so this particular third one, this is the third one here. If you take this third one, so single row and the two columns have been, so two columns in the sense these two columns have been taken into consideration. So therefore you can see this will be taken as so A will be the row element and the column common element will be B here. Common element will be B here. Okay, common element will be seems something like that B here. So therefore, if you are trying to draw the what do you call logic diagram for this one, logic diagram is very much simple, pretty much simple here. So how could you draw this one here is, so this is the way you can draw. Look at this. So this one is A exclusive of B exclusive of C. Let me take first. So this is A and this is B here and this is C here. Let me draw some more lengthy. Okay, this is C here, for example. And here it is A exclusive of B, A exclusive of B, whatever the outcome you got here, this outcome is going to take the exclusive of with C here. So this is the, so here it is A exclusive R of B here, and this is A exclusive R of B exclusive R of C. So will be equal to sum. So this is what about sum, which we have to draw. And if you take what you call C, if you take the C value can be seems, so A into BC into AC into AB, BC into AC into so AB. So if you want to perform this particular operation, you could able to do something like this here. So BC, first one is AC. Let me take AB first. AB first. Let me take some other color. Then I could able to draw in a proper way. So this is A. This is B here. These two will be added together. Will be 1. Then followed by AC. Then followed by AC here. So AC in the sense, let me draw this particular A first. Furthermore, this is A and this is C here. This is C here. So this will be considered as AC. And let me draw, so this B some more. This B some more here. So this is B here, B, and here it is C. So will be taken this one here. And all these are together. Let me draw very smaller one. Then it is very easy to understand. So this is what the point which we have to consider in terms of this one here. Okay, this is the way. This is the way you can able to draw. So the logic diagram. Logic diagram will be seems something like this here. Okay, if you have any smaller doubts, you can eliminate in a formal way. You can draw. So pretty much good lines. Then it's very easy to understand. So from here to and so on, and here you can draw. Here you can take. So that is what. Okay. This is full adder. This is full adder. So full adder will be taken. So while evaluating the sum is very, very important while writing full adder here. Evaluation of this particular thing is very, very important. So this is expected from your so evaluator or during your final examination. During final examination, it is being expected. Okay. So this is what about full adder here. And multiple bit. So next topic will be multi-bit adder. Not only 2 bits or 3 bits. If you have number of bits are there with you, how could you add them? How could you add them? So if you have many number of bits which are available with you, so how could you add them here is, let me say, the output will be seen some, I mean the explanation will be seen something like this. For example, so 101101. Look at this, how many number of bits are available here. So 10, so 1100. For example, this is the particular thing which we have to available here. Look at this here. Always while we are adding two different bits, we maybe have some kind of so carry. So look at this, 1 plus 0 will be equal to 1, sum will be equal to, let me write carry here. Let me write carry at this particular place, and let me write sum at this particular place. This is sum, and also final carry. Let me write here. This is a final carry. Final carry. Carry at this place. Look at this. There is no carry for this particular thing right now. There is no carry for this particular thing right now. But second bit, so 0 plus 0, there is no carry again. Third bit, yes, 1 plus 1, there is a carry, and 0 will be the answer for that. Now here, up to this particular thing, this one will be taken only half adder. But if you consider 3 bits are there here, 3 bits are there here. Since 3 bits are available, so this will be taken. One is the sum, and the carry is 1 here. And here also 3 bits are available. At this place also 3 bits are available. 0 plus 0 plus 1, 1 is sum, and the carry will be 0. And here, so 3 bits are available here. So 0 is sum, and the carry will be, extra carry will be this one. This is extra carry. Look at this. So always to add number of bits, we may require so full adder. We may require full adder here. So how this could be gets added together here? Let me consider this is A, and this is B. This particular thing, all these things are C ins, and this is final carry. This is final carry. Okay. Now, if you consider in such a way that, so this particular element will be to a power. Let me say, this is 0th position. This is first position. This is second position, third position, fourth position, fifth position. So therefore, you'd like to write it as A0, B0 is the first one. So these two are A0, B0. Okay. A1, B1 will be the second bit positions, and so on and so forth. Based on this one, so how this could